Thank you for coming back to our video series, and welcome to our video on rates and related rates. So first, before we move on into rates and related rates, I want to quickly go over another example problem of optimization, which will kind of feed into our topic of rates and related rates. So our first problem is the following. We have a long straight wall, and we want to put up a fence that surrounds a rectangular area against this wall. So we don't want to put any fencing against this wall, and we have our fencing having length x and width y. So we can find that the perimeter of our fencing is 100. We want to find, we have 100 meters or feet or whatever, 100 feet of fencing that we want to use up. So we have 100 feet of fencing that we want to use up. X plus 2y equals 100. And we also know that the area is equal to x times y. So what we want to do is maximize the area. So we want to find dA dx is equal to, we're going to be using the product rule and the chain rule here through implicit differentiation. So first we want to take the derivative of x. So the derivative of the first term is 1 times y, the second term, plus the derivative of the second term, which is dy dx, times the first term, which is x. And since we want to optimize a, we have to set the derivative of a equal to 0. And that gives us a value, dy dx is equal to negative y over x. Now we want some way to get this expression into here. So what we need to do is implicitly differentiate this now. So we end up with d dx of x plus 2y equals 100, parentheses outside of the 100. So the derivative of x is 1 plus 2 dy dx equals 0. And we can plug in dy dx from here. So 1 plus 2 times negative y over x equals 0. And we end up getting 2y equals x. So if we plug this into the expression, x plus x equals 100, so x is equal to 50 feet. And then we plug this back in to find y. 50 plus 2y equals 100. 2y equals 50, so y is equal to 25 feet. So this is equal to 25 feet, and this is equal to 50 feet, and we have optimized the area. So now we are going to look at rates and related rates. So the first problem is that a spherical snowball is melting. Its radius decreases at a constant rate of 2 centimeters per minute from an initial value of 70 centimeters. How fast is the volume decreasing half an hour later? So we first need to find a value of r. We need to find the function of r with respect to t. So we know that the initial value of r is 70, and we know that the rate of decrease is -2. So we have 70 minus 2t, and this is centimeters. Now we also know that v equals 4/3 pi r cubed. So, there are a few things that we need to first find. So dr dt, the rate of change, is equal to -2 centimeters per minute. And we need to find dv dt is equal to 4/3 pi times 3r squared dr dt. So what we need to do is plug in our r function into here, plug in our rate of change here, and we will obtain an expression for dv dt at time is equal to 30 minutes. So we want to find the rate of change of the volume after 30 minutes. So dv dt after 30 minutes is equal to 4/3 pi times 3 times 70 minus 2 times 30 squared and then we close that up times the rate of change times -2 centimeters per minute. So after evaluating this, we end up with -800 pi centimeters cubed per minute. Or approximately -2,500 cubic centimeters per minute. Now there are some cases where we can't determine a time dependence relation, so what we need to do is use a related rate problem. So an example of a related rate problem is the following. A spherical snowball, so this is another spherical snowball problem, melts in such a way that the instant at which its radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. At what rate is the volume of the ball of snow changing at that instant? So let's rewrite this. So we have v equals 4/3 pi r cubed. Now we don't know anything about the relation between, we don't know any time relation of the radius. But we do know that dr dt when the radius is 20 centimeters is equal to -3 centimeters per minute. So what we need to do is differentiate this again. So we have dv dt equals 4/3 times pi times 3r squared times dr dt. Is equal to 4 pi r squared dr dt. So we have a radius, r is equal to 20 centimeters, and we have a rate of change -3 centimeters per minute. We don't have anything else. We don't know a time relation between, we don't know the time relation of the radius, as I mentioned earlier. So what we have to do is basically just plug and chug our values. So we have dv dt is equal to 4 pi times the radius squared times the rate of change is -3 centimeters per minute. And that is equal to -4,800 pi centimeters cube per minute. So there are two ways that you can determine rates. The first way is by modeling two different functions where we have an initial function, in this case the volume, and we have some other function, r. And we also have a time dependence of r. So we can say that we have v equals 4/3 pi r of t cubed. In the first case, we knew that it was a constant rate, so we could easily model that using a function. Here, on the other hand, the only thing that we knew is that at the point where the radius is equal to 20 centimeters, the rate is -3 centimeters per minute. So as long as we know a rate and we know some function, we should be good. And you can do basically any related rate problem using this technique. So thank you for watching this video. I look forward to having you back for our 10th video in this series, where we'll be discussing L'Hopital's rule, which is a technique for determining limits. So thank you for watching, and I look forward to seeing you in our next video.